Okay, so we're going to talk about energy changing form today. Changing forms, okay? So let's just consider this example for a second. All right, let's say we got a nuclear power plant, all right? And the point is to ultimately get to this, all right, electricity, okay, and light, all right? Now, when we split large atoms like uranium, okay, they do that, by the way, by firing protons at these big atoms and they split. And then what do you get? You get lots of little pieces, okay? And in addition to that, you get energy, okay? And that energy comes off of here directly in the form of heat, okay? The environment warms up where this reaction's happening. And what is it that we warm up with that nuclear power, nuclear energy? Water. Yeah. Okay, we warm up water. All right. Turns into steam, okay, which is just water in the gas form. And it goes through a big fan, and that turns a generator. Okay, that generator produces this, and then we get that. Okay. Now, does all of this energy make it into electricity and light? No, there's some lost energy along the way, okay? But it's not lost in the universe, okay? It's lost to the system. So this system loses energy, and that wasted energy just goes into heat, okay? It like just warms up the surroundings, but it doesn't make it to here, okay? We're always trying to get to be more efficient, all right? The more of this we can get to here, the better, right? Okay, efficiency. And energy, the energy sector is always going to have jobs. Okay, they're always going to be hiring people to try and get more of this to this, whether we are doing nuclear or, some other clean forms of energy or burning stuff. Okay, we do that still, don't we? Okay, what kind of stuff do we burn? Coal, natural gas. Okay, primarily. All right, so let's kind of connect this back to last time. All right, we know about work. We know that power is how quickly work gets done. That's where the time comes into play. And now let's connect it to energy. So energy, if we have this, we can do work. Okay, very simply, if I take the football and I ate some breakfast, so I got some energy, now I can do some work. Okay? That's how energy is connected in. These are both measured in what? Joules. Okay? All right, they're not the same thing, they're just very connected. Okay? If you do work, it takes energy. All right? If you have energy, you can do work. Okay, and we did that last time. We'll skip through that quickly. Okay, new stuff today we want to be able to do. We want to identify different types of energy. And we already did some of that on the first slide. We're going to do examples of energy being conserved. These are the two types of energies we are going to deal with mostly, kinetic and potential. Okay, very quickly, kinetic, all right, that's the energy of what? Anything moving. Okay, potential energy has to do with gravity, how far something is above the ground. Okay, has to do with gravitational fields. We'll get into that. And then we want to be able to calculate them and deal with the math of these things. Okay, there's a spot in your notes for you to write down the conservation of energy note. Okay, energy changing forms. Here we go. All right. There is some lost energy here. Okay, conservation of energy says that energy can't be lost though. Okay, now this system loses energy, but does the planet lose energy? Not really very much. Some might get reflected into space, but what I'm saying is not all of it gets here. Okay, there's some wasted energy due to heat. All right, but it's still conserved, okay, in the global sense. All right, how many people have been winter camping? Anybody? It's not that fun, okay? All right, but even in the summer when it gets really cold at night in the mountains, okay, you got to eat a lot of carby, fatty foods, all right, because that helps you do what? Helps you create heat and stay warm in your sleeping bag, okay, chemical to heat energy. All right, we also take chemical potential, all right, and our cars can do work. If we have this, we can do work. Dynamite, it's got chemical potential, thus the ability to do work. Pretty much everything we do takes chemical potential and allows us to do work. Again, burning stuff, chemical potential, will do work on these fans, okay, turbines, all right, and then we can go to other types of energy. Okay, even sound. All right, what is sound? It's waves, but what are waves? What are mechanical waves? Okay, think small. Think invisible. Okay, really it's just air particles moving around all over the place. Okay, which is really actually just kinetic energy. Okay, moving stuff. So moving air particles back and forth. All right, subs. All right, tweeters. Okay, that's just fluctuating air. That then does work on your ear, on the parts in your ear, and your brain picks that up. Okay, this one we're going to camp out on a little bit longer. Gravitational potential. That's a big deal. We're going to study that heavily in this class. Okay, so let's start out with this. Why do we build dams? Big dams like the Hoover Dam. Okay, what's the purpose? There's really two. Okay, two main purposes. All right, what's one? Okay, yeah, that's kind of like a third, like flood control. Okay, that wasn't one of the ones I was thinking of, but yeah. Okay, what else? Okay, clean power. All right, that's good. Okay, so water goes down through these tubes, okay, and turns a fan, creates clean electricity. All right, and what's the second big one? Okay, Monique? Yeah, it's just storage. Okay, it's just a big bathtub that stores water. Okay, now rafters like me, we don't like dams because look at all that river that I can't raft now. It's underwater. Okay, but they do some good stuff for us, but you know, there's drawbacks as well. Okay, so to electrical energy, all right, there's Las Vegas. Okay, you guys been to Las Vegas? Anybody? Okay, all right, it's kind of a cool city, lots of lights there, all right, electrical energy from gravitational potential. Okay, so we take water from up here, put it through fans, all right, and then we get that electrical energy. Okay, this is Yosemite. I'm going to skip through this slide real quick. Okay, let's say you climb from down here up to here. You guys have seen this picture before. Okay, if you're down there and you get up there, what did you have to do to get up there? You had to do work just like in your People Power Lab. Okay, now that you've done that work, you have gained a type of energy. What type of energy is that? Potential energy. So here's the definition, all right, in your notes. Gravitational potential energy we get by doing mass times gravity times height. Okay, then there's a blank that says or. We're just going to shorten this to MGH. Okay, so down here, PE equals MGH. This is what we use to abbreviate potential energy. Makes a lot of sense. Okay, Mass times little g, acceleration due to gravity, and height. These are the things that potential energy depends on. All right, so if we lift a more massive object, we got more joules of potential. Let's say we are on a planet that has 2 times our little g. All right, lots of acceleration due to gravity. Okay, if we lift an object on that planet, okay, we're going to have more potential energy if we lift it at the same distance. Okay, and then the higher you lift it above the ground, or whatever we define as the 0 point, that affects potential energy. Okay, now check this out. The work equation, do you guys see how the work equation is sort of hidden within the potential energy equation? Okay, so if I exert a force equal to the mg of this ball, okay, mass times gravity, the weight of this ball. If I exert that force over a distance, I just did work, and now we have potential. Okay, so the work equation is right there within this. Okay, here's the force. Okay, units. If you break it all down, all right, here's the fundamental units. You don't need to write that down. Okay, you just need to know that it's measured in joules. In fact, all energies are measured in joules. Okay, now, you might have to deal with a unit like calories, okay, or kilojoules, all right, but those are all still just energy units, okay? All right, let's talk about the energy of moving stuff. Here's the equation. It is 1/2 mass times velocity squared. Okay, shortened into variable form. And what do you suppose this is measured in? Also joules. Okay, so real quick example of energy conservation with these two types. Okay, let's go back to the hiker example. Let's say we're going to climb a mountain or a 14er. You guys climbed a 14er before? Anybody climbed a 14er? Okay, like a few of us? All right. It's a good thing to do when you live in Colorado. Okay, at least once. Okay, so this is Long's Peak right here. So we're a portion of the way up the hike. Let's say that, yum, we're going to eat some pancakes. Okay, there they go. The hiker now has the ability to do work. Okay, so here they go. They're going to climb. And let's focus on the backpack here. Okay, so 10,000 joules, let's say, of work were done on the backpack to change its position. Okay, that was what your YouTube notes were last night. Okay, now that we've done that work, what does the backpack possess? Potential energy. And it's got 10,000 joules of potential energy. It's the same. Okay, let's say the backpack accidentally, okay, watch it, gets kicked off the side of the mountain. Okay, or maybe they didn't want to carry it down, so they just threw it and thought they'd pick it up later. Not really a good idea, but. Okay, right before it hits, okay, it's moving right there. Right before it hits, it's got 10,000 joules of what? Kinetic energy now. It's moving. Okay, what about midway down? That's right, it is half and half. It's got half, so it'd have 5,000 joules of potential and 5,000 joules of kinetic. Okay, now when it hits the snow, where does the energy go? Okay, energy is conserved on a big scale, but for the backpack, energy is not conserved. Okay, the energy sort of gets wasted. It warms the snow up a little bit, it throws snow around. Okay, it might make some sound, So really it's just molecules jostling around. We call that heat. It's wasted energy. We can't do anything with it. Okay? All right, so in summary, okay, these are the things that we know so far. Okay? And we're going to deal with conservation of energy problems next. Some things you might want to write down. You will see this on maybe UT homework. You will see it in books. I like to say PE because it makes a lot of sense to people. But you will see capital U. That's another symbol used to abbreviate potential energy, so be aware of that. Also, textbooks like to abbreviate kinetic energy just K. So don't be surprised if you see that. All right, AP next year, okay? AP likes to use these symbols. Okay, so there's a lot of misconceptions on energy conservation, okay? There's a lot of things that, that probably the general public don't get on energy conservation. So a story for you guys. I used to guide rafting trips back in the day, and people would come to us from very flat states, okay, like where? Yes, Texas, Kansas, Iowa, okay? All right, they want to get a big river experience in, okay? Mountain experience, yeah, let's do it. Okay, so they'd come and we would always get these same 3 really weird questions. Okay, it wasn't just me, it was like all the guides would hear these questions. And the first one was we'd push the boats off the ramp and we'd be going down the river and they'd be all pumped. All right, first like couple minutes of the rafting trip and they'd look in the water and they'd be like, "Where are the tracks?" I know, we would never think that because we're from Colorado, but they literally thought that the raft was like an amusement park and was going to go down like Pirates of the Caribbean at Disneyland, okay? And this isn't just like kids. I mean, I understand if kids ask it. This is like adults and teenagers and everybody would ask this. Okay, second question that we get over and over. This one's really going to blow your mind. But we'd be going down and our job was also to like point out like the different plants and animals and whatnot. And so we'd be like, "Oh, there's a deer right there." And people would ask, "At what elevation do deer turn into elk?" Okay, common question, like at some point, you know, the deer were just going to magic elevation, they were just going to get bigger and taste better all of a sudden. Okay, people think this stuff. And the third one violates energy conservation. Okay, so at the end of the trip, they'd be getting kind of cold, maybe ready for the trip to be done, and they'd say, "So when is the river going to bring us back around to where we started? When are we going to go back to that starting point we were at?" Okay, you guys see any energy problems with that? Okay, rivers operate on an elevation loss, okay? It is this turning into that, correct? Where do rivers flow in circles, however? Lazy rivers at water parks in Texas and in Denver. All right, okay, oh, and at Fruita Rec, right? Don't we got a little mini lazy river? Okay, but energy has to be pumped into the system using electricity and a pump to get that to happen. Okay, so what I'm trying to tell you guys, there's a lot of misconceptions about energy. All right, and you guys might think that's a pretty dumb thing to think. However, you guys were from a mountain state, right? Okay, but we would still hope that people would know that. I mean, it's kind of basic, but okay. Okay, so we are going to do some stuff with roller coasters. Okay, roller coasters operate heavily on energy conservation. Okay, what type of energy do you have at the top of a roller coaster? Potential and probably a little bit of kinetic too, because it is moving. Okay, and then that potential turns into kinetic. Now we could do roller coaster problems with forces and kinematics, okay, which we already know how to do, but energy actually makes it easier. Okay, so we're going to learn some new physics tactics here. Okay, so let's look at this roller coaster here. All right, where would we have the greatest speed? Is it B? Because C's got a little hill. Okay, answer is actually D. Okay, energy conservation. Yes, we're going to slow down a little bit here, but energy conservation says that we would have the same speed if the roller coaster did that as if it does this. Okay, now in reality, the speed is going to be a little different because the friction on those two paths might be different. Okay, but if we are leaving friction out of the situation, which we sometimes do, then D would have the greatest speed. Okay, let's do a little quiz here to see if this makes sense. Okay, let's put numbers in here. So we have these different amounts of joules, okay, really easy numbers. And let's say at the top, it's moving. So what's our total energy at the top? 55 joules. Okay, what is going to be the kinetic energy at point B? Assuming no energy is lost, what is the total energy at B? 55. Okay, so the kinetic would be 35. All right, 20 plus 35, 55. Okay, what's the kinetic energy at C? 25. It's going to slow down a little bit because it's got to go back up and convert some energy back into potential. Okay, how about D? Got 45 joules, and so on. These just add to 55 each time. Okay, now let's put a taller hill in here. Let's put that. Let's say that the potential energy would be 60 at the top of this. Is the roller coaster going to make it up there? Okay, not without some help from a motor or something like that. Okay, it would make it to this potential energy line. Okay, so we're going to do a problem with this. This is the Steel Dragon. I believe it is in Japan. Yes, it's in Japan. Field trip? Go ride the Steel Dragon in Japan? That sounds feasible, right? Okay, so let's put some numbers to this. These are actual numbers. Okay, and I think at one point it might have been the tallest roller coaster. Okay, there's different, but this is in 01, so I don't know. Okay, 93.6 from the bottom of this track here. All right, from the top down here. So we're going to start up here. We're going to assume the roller coaster is going 0 meters per second at the top, and we're going to solve for the speed down here. Okay, so in your notes it says PowerPoint example. Okay, and let's work this one out. Here's how all of our energy conservation problems should start. You're going to put the type of energy you have initially, and you're going to put the energy you have at the final point. In other words, EI equals EF. Okay, so we have all potential at the top, all kinetic at the bottom. All right, now we're going to sub in some equations. Okay, here they are. Well, there goes the roller coaster. Here's our potential equation. Here's our kinetic equation. Now, if we want to solve for velocity, anybody see any kind of problems with this a little bit? We have little g. We have the height. Yeah, there's no mass given to us in the problem. Okay, anybody see any algebraic solutions to that? Chloe? They do cancel. Okay. There's an m on both sides, so they go away. This means that an empty roller coaster or a roller coaster full of people will have the same speed. Okay? The mass does not matter in this situation. All right, that's also true if we drop something. If I drop a football and a golf ball, Won't they have the same speed at the bottom? Okay, and we studied that in kinematics. All right, here we see mass canceling again. Okay, question? Alexa, do you have a question? Okay, great question. The 1/2 stays. There's nothing that cancels out the 1/2. All right, so let's plug in some numbers. We can multiply the 2 to the other side. Okay, so we have 2GH. Or you could divide by 1/2, same thing. Okay, now how do we get V by itself? We got to square root our final thing. So in PowerPoint here, we got the numbers. All right, we're going to end up square rooting that. So plug that into your calculator and prove the answer. Okay, we're going to keep doing problems kind of like this.